Welcome to the deep dive. So, if you've ever had to run a really complex simulation, maybe for training a sophisticated AI or, modeling a large physics system, you know that the quality of your input data is just everything.
Oh, absolutely. Garbage in, garbage out.
Exactly. And in high dimensional math, it turns out the most popular input method, just simple random sampling, is often, well, it's often garbage.
It really is. Randomness sounds like it should be fair mathematically, but when you actually compute it, it can be a disaster.
So,
You get these massive clusters of points all bunched up, and then somewhere else, these huge empty gaps that you're not accounting for at all. That lack of uniformity, it creates real inefficiency and introduces significant computational error.
so our mission today is to explore what the source material calls the quest for uniformity.
Mm.
It's about how mathematicians and computer scientists have figured out how to generate these perfectly spread out, deterministic point sets, even when the geometry gets incredibly weird, like on an n-dimensional sphere or a hypersphere.
And we're going to dive into a really novel principled approach that, kind of solves this problem. It's based on some classic number theory sequences, but it uses this elegant recursive framework that's built specifically to respect the tricky surface area of a sphere.
And the relevance here is huge. We're
Yeah.
talking about something called low discrepancy sequences, or LDS.
Uh-huh.
Getting these right is a total game changer for everything from numerical integration to optimization and advanced engineering.
It is. This new method really provides a superior scalable blueprint for guaranteed uniformity in places where, frankly, randomness just won't cut it.
Okay, let's unpack that foundational concept then. Low discrepancy sequences. What is the real functional difference between an LDS and just random chance?
The functional difference, it really comes down to reducing error. Imagine you're trying to find the area under a curve, but you're doing it in, say, 10 dimensions. If you sample that space randomly, those clusters and gaps we talked about, they lead to a huge variance in your estimate. And LDS, on the other hand, it just eliminates that variability. It makes sure that every little part of the space gets sampled an equal number of times.
I'm picturing it like throwing darts.
Yeah.
A random thrower makes a total mess of the board, but an LDS is like a perfectly programmed machine where every single dart lands exactly where it needs to maximize the spread.
That's a great visual for it.
Yeah.
And that smooth, uniform distribution, that's one critical property. But for it to be really useful in a serious simulation, an LDS needs to have two other things going for it.
And what are those?
First is determinism. The sequence is generated by a fixed algorithm, not by chance. It's absolutely non-negotiable if you want reproducibility in an experiment.
Right, so you can run the simulation again tomorrow and you get the exact same result.
Exactly. The second is incrementality. This means you can add new points to your set without having to throw out all your previous work and recalculate everything.
That seems crucial for optimization algorithms, right? The ones that run for hours and just keep refining the sample size.
Precisely. It's vital when you're dealing with these really complex high-dimensional spaces.
So where does this kind of precise uniformity actually show up? In high-stakes fields.
Well, think about robotic motion planning. To design a robot's path, you often have to sample the space of all possible 3D rotations. Mathematically, that's represented by something called SO3, or the three-sphere.
Which is not a simple space.
Not at all. It's made of unit quaternions, four-dimensional coordinates for tracking rotations. Now, if your sampling method clusters points on that three-sphere, your robot might just test the same few rotation parameters over and over again, while totally ignoring huge other possibilities.
So bad sampling literally means slower, dumber robots. Slower, dumber, and less efficient. It's also critical in wireless communication for MIMO systems. They use these uniform points as code words to maximize signal separation. And in machine learning, if you normalize your parameters, you are essentially projecting them onto a hypersphere, and you need uniform sampling for unbiased training.
Okay, so we know why we need it. Let's get into the how. Where do you even start to build a system that can achieve this?
You have to start small, really small, with what the source material calls the foundational atom, the van der Korpit sequence.
The VDC sequence. I love this one. It's so simple, but so clever. It generates perfectly uniform points, but only on a 1D line from 0 to 1. Can you just remind us how that base reversal trick works?
Sure, it's constructed by taking the natural numbers 1, 2, 3, 4 and
What?
reversing their base dollar representation. Usually Babelers is a prime number.
So let's use base 2. That's the easiest.
Okay, base 2, the number 1 is just 1 in binary. You reverse that, put a decimal in front, you get 0.1 in binary, which is 0.5. The number 2 is 10 in binary. Reverse it, you get 0, 1. So 0.01 in binary, which is 0.25.
3 is 11.
Right. Reverse that, it's still 11. So 0.11 in binary, which is 0.5 plus 0.25. That's 0.75.
So just with the first three numbers, we've already hit 0.5, 0.25, and 0.75. You can see them immediately spreading out to fill the biggest gaps on the line.
Exactly. Compare that to 3 random numbers, which could all land, below 0.1.
Yeah.
The VDC sequence guarantees low discrepancy in one dimension.
So that's our blueprint for a line. How do we scale that up to fill a 2D square or an n-dimensional cube?
That is the job of the Halton sequence. It's just a direct extension of van der Korput to multiple dimensions.
Oh, you just use more of them.
Basically, yeah.
Yeah.
To generate a sequence for, say, d dimensions, you just use d separate VDC sequences. The one catch is that each sequence has to be generated using a different prime number as its base.
So for a 2D square, I might use base 2 for my x-coordinate and, say, base 3 for my y-coordinate.
Exactly. And the combination of those two independent, uniform prime base sequences gives you points that are spread uniformly across the whole square. It's a cornerstone of what's called quasi-Monte Carlo methods.
But this is where the real problem starts, isn't it?
Yeah.
We don't really care about flat cubes. We're interested in spheres, curved surfaces. What happens when you try to just slap this Halton blueprint onto the surface of a ball, a two-sphere?
It fails. It fails miserably. That is the core challenge. You can use standard methods like cylindrical mapping or Hopf coordinates to map flat points onto a sphere, but they create massive distortion.
Do you give us a visual for that distortion?
Think about latitude and longitude lines on a globe.
Okay.
Near the equator, a square of 1 degree by 1 degree covers a pretty big area, but now go up near the North Pole. That same 1 degree longitude change covers a tiny, tiny distance.
I see. So when you map a perfectly even grid from a flat square onto the globe, the points get massively crowded together near the poles where the surface shrinks.
Precisely. The points bunch up, creating huge clusters. You get high discrepancy, which completely defeats the purpose of using an LDS in the first place. And the reason is purely geometric. The flat mapping just fails to account for the differential geometry of the curve.
So this is the aha moment. Simply mapping coordinates isn't enough. You have to somehow respect the geometry itself. You have to respect the surface area element.
Absolutely. Uniformity requires that your math has to actively compensate for how the local area expands or contracts across the surface. And this gets really, really hard because the complexity of that surface area element, it just explodes as you add dimensions.
Let's ground this in a simpler example before we go to hyperspheres. The source talks about a 2D unit disk. How does compensating for surface area work there?
Right, so on a flat disk, we use polar coordinates, radius, and angle. As you move out from the center, the circumference gets bigger, right? The area element is $RDR d theta high. That WART term is the key.
Because if you just sample the radius r linearly, you'll get a dense cloud of points near the center where the area is tiny.
Correct. So to compensate for area growing with r, you have to sample r non-linearly. You use the square root of the VDC sequence. So r, RRT, VDCK, B2S.
And the square root function pushes the points outwards towards the edge where there's more area to cover.
Exactly. It forces the points to spread out, guaranteeing a uniform distribution across the whole disk.
Okay, that makes the principle really clear. The sampling has to be the inverse of the area distribution. But if you need a square root for a flat disk, what kind of monster math are we looking at for an n-sphere?
The complexity just skyrockets. The surface of an n-sphere, it needs n coordinates, basically n angles. And the surface area element, the dollars, is defined by this huge product of sine functions of all the different angles.
That sounds like a trigonometric nightmare to integrate. You can't just use a single square root function anymore.
You can't, and that's the point. Trying to integrate that n-dimensional thing all at once is mathematically intractable. And this is why the approach in the source material is so significant. They figured out how to generalize this principle using a really elegant recursive framework.
Okay, let's step into that breakthrough. How does this new algorithm handle that massive trigonometric product in the surface area element? Why recursion?
Recursion is the key because it breaks this supercoupled n-dimensional problem into a sequence of much simpler one-dimensional problems. The algorithm doesn't try to solve the whole thing at once.
So instead of trying to tackle the whole n-sphere, you start small and you build your way up.
Precisely. You initialize the points on the lowest dimension, which is $7.1, a simple circle. Then you iteratively add one dimension at a time. You go from the point in n dimensions to the new point in null dimensions.
What's the critical step inside that loop?
The core of it is defining a special integral function, 5JLR, for each new angle you need to find. And here's the clever part. This function, 5J, is itself computed recursively. It depends on the function from the dimension before it.
Wait a second. So 5J$ is defined to solve the geometry problem, but because of the recursion, it's not trying to solve the whole n-sphere problem at once. It's just solving for the current angle, knowing the previous ones are already uniform.
You have absolutely nailed it. That recursive definition lets it correctly integrate only the relevant local part of the surface for that one angle, guaranteeing the uniformity from the previous steps is preserved. It decouples the complexity.
That feels so much cleaner than trying to wrestle with the whole thing at the same time.
Yeah.
So once you have this recursive function 5J$, how does it connect back to our building block, the van der Korpet sequence?
You take a new VDC sequence and you map it into the range of that function, 5J$. This forces the density of your sampled points to perfectly match the nonlinear density that the spherical geometry requires at that particular stage.
And then the final step is to find the actual angle, the theta j. How do you do that?
By doing the inverse operation, we need to find thethado, happily. We need to find thetaj fj1. And this is where theory meets reality. While fetish is defined by a nice integral, calculating its inverse function analytically is often impossible. The terms are just too complex.
So the beautiful math hits a computational brick wall. How do they handle that inversion efficiently in practice?
They use a pre-computed lookup table and interpolation. It's a very practical solution. You calculate a bunch of pairs of ahead of time and store them.
I see.
Then when you get your VDC value, you just find it on the table and use interpolation to get a very good estimate of the angle theta GM again. You don't have to solve the impossible inverse function every single time.
It's a brilliant mix of theoretical elegance and practical engineering. Use recursion for correctness and interpolation for speed. But theory needs proof. How do they show that this method actually beats the old ones, like the cylindrical or Hopf coordinates?
They prove it quantitatively with numerical experiments using a metric called dispersion.
Okay, we need a clear definition of dispersion. What are they actually measuring?
Dispersion is a measure of the geometric quality of the point set. They calculate it by first building the convex hull of all the generated points. The convex hull is, think of it like tightly shrink wrapping the sphere. The flat faces of the shrink wrap define the hull.
Okay, so you have this geodesic structure made by connecting all the points on the sphere.
Exactly. And dispersion then measures the difference between the maximum and minimum angular distance between neighboring points, basically the size difference between the biggest and smallest faces on that hull.
So low dispersion means all the faces are about the same size, which means the points are perfectly spaced out.
You got it. High dispersion means you have big gaps right next to crowded clusters.
That makes a lot of sense. So what did the visual proof of this convex hull actually show?
The visual contrast is really striking, especially on the 3-sphere, 3s $3. When they generated 600 points with the new recursive method, the faces of the hull were noticeably more regular, more uniform in size.
And the random method?
A total mess. Highly distorted faces, indicating huge variations in the distances between neighboring points.
The visual's one thing. What are the hard numbers, the dispersion results?
The proposed method consistently achieved the lowest dispersion, across the board. Compared to random sampling, cylindrical mapping, and the Hopf coordinate method, this recursive approach was measurably significantly better on 3383.
And does that advantage hold up as you go to higher dimensions? Because that's where things get really tough.
That's the most critical finding. The research confirms that yes, the superior performance is maintained and it scales effectively in higher dimensions, specifically C14 and SIFTI $5. It really proves that the principled surface area-based math is just fundamentally better than the old ad hoc mapping.
So the final verdict is that we have an elegant mathematical solution that respects the geometry, is deterministic, and is now proven quantitatively to generate a more uniform distribution than anything else, especially in these really challenging high dimensions.
It's a profound contribution, really. It gives people a generalized, uniform point distribution that's not just mathematically pure, but it's also simple enough to be turned into an efficient, production-ready code using things like lookup tables.
And there we have it. We started with the simple 1D van der Korpet sequence, and we used those principles of base reversal and geometric compensation to solve this incredibly complex puzzle on an n-sphere. We now have a truly reliable, deterministic, and scalable way to seed the most sophisticated systems that modern science and engineering depend on.
The impact of replacing chaotic, error prone randomness with guaranteed scalable uniformity, I mean, it can't be overstated. It fundamentally changes the efficiency and the trustworthiness of simulations, cutting computational costs while increasing our certainty in the results.
So here is the final thought we want to leave you with. If achieving this kind of uniform, deterministic sampling can so dramatically increase reproducibility and slash errors in our simulations today, what previously intractable multidimensional problem, maybe in quantum physics or global climate modeling or complex finance, could suddenly become solvable tomorrow, simply by replacing the role of a random dice with a guarantee of geometric uniformity. Think about that kind of breakthrough as you step back out into the world.